Hello all. Today we're going to be looking at the life and death of stars. We're going to be talking about how stars die and how, what happens when they die, what determines how they will die, and such like that. I wanted to show you, this is an XK City comic. It's an expanded Hertzsprung-Russell diagram. The key is expanded here. The top part of the Hertzsprung-Russell, let's say right here, this should be very familiar to you. This is our basic Hertzsprung-Russell. We have the main sequence. We got the white dwarfs. We got the giants, supergiants. This is Betelgeuse, I think one of the biggest stars. I think VY Canis Majoris. By the way, big stars don't last very long. I'll talk about that later. So here's the sun right in the middle of everything, perfectly average star. Then it lists some other stuff. For example, interior of a hydrogen bomb during detonation. Huge amounts of temperature, not as much luminosity. I mean, compared to a sun, Here are planets. Thankfully, our planets are down around the 300 Kelvin range. That's a lot more livable for us. Nuclear fireball, lightning bolts, lava lakes, cruise ships, and an astronomer. So here's you. You are down here, again, about 300 Kelvin, somewhere in that range, but you do not have a very large luminosity, I'm very sad to say, mostly due to your size. Even though a blue whale is a little colder, it's a whole heck of a lot bigger than you are. So sort of an interesting little graph to look at. But the Hertzsprung-Russell diagram allows us to talk about what happens to stars. Let me find here's a good Hertzsprung-Russell diagram that's a little more illustrated. Enlarge this a little bit. So again, on the x-axis, we have our temperature. It is measured in Kelvin, as are all temperatures. As are all temperatures in astrophysics. And then on the y-axis, we have solar luminosity. This is a logarithmic scale. It may not look like it. You see, 0, 1, 2, 3, 4, 5. But think about it. This is 1, 10, 100, 1,000, 10,000, 100,000, million. And then the x-axis is also measured logarithmically. Notice how this would be a 20,000 Kelvin gap, and this is a 3,000 Kelvin gap. We have our main sequence, our white dwarfs, our giants, and our supergiants. So let's talk about how stars die and why they die. So let's look at our sun right now. We got a pink sun, I guess, right now. We have the core of the sun, and we have the outer layers. Now, I'm not going to be able to go into as much detail as they do in some other videos, so I'm going to link 2 other videos I would like you to watch. They're crash course videos about astrophysics, and they do an amazing job of talking about this. I'm just going to talk about it pretty briefly and highlight some important points. So, right now, our sun is busy burning away hydrogen. The core of the sun has a bunch of hydrogen in it, and due to all the gravitational force pushing in on the core based on gravity and all the mass of all the other gases there, it is causing that hydrogen to fuse into helium. So 2 hydrogens smash into each other. I'm highly simplifying stuff here. Form a helium and energy. We're going to go into a lot more detail in the nuclear chapter, but for now, that's good enough. So this leads to a question. Right now in our sun, our hydrogen is turning to helium. Well, okay. What happens when the hydrogen runs out? What happens when that hydrogen runs out? Because there's a finite amount of hydrogen in the core of the sun. It's not going to be around forever. Right now, our sun is in that main sequence. It's happily burning away its hydrogen. And so let's think about what's going to happen as it starts to run out of hydrogen. Well, first thing that's going to happen is right now that nuclear radiation is providing an outward force. As soon as you start reducing the amount of nuclear fusion available by lowering down the amount of hydrogen atoms, you're going to see that star begin to shrink. It's going to start squeezing down. It's going to start squeezing in on that core a little bit more because gravity is going to start winning that tug of war. Right now, the tug of war is a tie between gravity and radiation. But as soon as you start running out of hydrogen and there's less reactions, gravity is going to start winning. And so gravity is going to start smushing on the core of that star even harder. It's going to push even harder. It's going to squeeze down a little bit, pull in a little bit harder. Now what that's going to do with the core of the star being squeezed even harder, now there will be enough heat and pressure to cause the heliums, which now you have a lot of, because remember, the hydrogen's turned into heliums. That's going to be enough heat and pressure for those heliums to start pushing out even more. And they are going to push out even more. The sun's going to start pushing out even more. It's going to start causing the outer, the sun to expand. It's going to be a lot more radiation. The sun is going to get bigger. As we start squeezing more in, now the helium starts going off. The star's going to get a lot bigger. Our Earth will start getting really big. As it gets bigger, all the energy that's produced, even though we'll be producing more energy, it's going to be spread out over a larger area, and so the star will begin to get colder. It's going to get bigger, but a little bit colder. And so what's going to happen? Let me actually pull this over here. I need to draw on the Hertzsprung-Russell diagram. That's tough to do on a colored diagram like this. Uh-oh, did I freeze things up? Hello. Uh-oh. Try that again. Oop. Okay, let's try that one again. I think I was being a little too crazy with my notes here. There we go. Let's just delete that, and let's put up here. All right. So our sun. Let's say our sun's hanging out right here. Okay. So it's going to grow. It's going to grow and cool, and so it's going to grow into a red giant. It's going to grow into a red giant as that helium begins to burn hotter and hotter and cause the star to grow and cool. Eventually, we're going to start running out of helium. As we start running out of helium, we may shrink a little bit, and then maybe another type of reaction may start. Maybe you'll start fusing into oxygen or carbon or bigger and bigger elements as you go forward. Eventually, though, we're going to get to a system where we just don't have enough stuff. There's not enough mass in our sun to keep squeezing bigger and bigger stuff together, fusing bigger and bigger things. So even though the star may oscillate back and forth a little bit as we start running out of one element, then fusing a bigger element, in our sun, once we have a bunch of oxygen in that core, really the sun doesn't have enough mass to fuse anything bigger. At that point, the star is going to start collapsing. And what will essentially happen is the core will just, over a few million years, it's just gravitational force going to be lost because a lot of mass is gone, and the outer layers of the star are going to start blowing away. It's going to start blowing away the outer layers. It's not a very dramatic process, but those outer layers of the star and all the gases in those outer layers are going to form what's called a nebula. It's going to form a big cloud of gas. It could even maybe form new planets and new stars in the future. Now, at that point, the only thing left is the core, and now that core will be a white dwarf. The core is still going to be burning hot, but it's going to be hanging out at the white dwarfs because it's going to be tiny. It's very hot, but it's very tiny. This is the path for our sun. And that's because the sun is not that big of a star. It is, by definition, one solar mass. And for anything that's, let's say, 8 solar masses, if our mass is less than 8 solar masses, this is going to be your path. The final product is going to be a white dwarf. And that's basically all that's going to occur. Those are the sort of boring ones. Let's talk about the more interesting stars. And again, this is where you really want to watch a video I'm going to link because they do a really good job of explaining this in a little more detail. But let's imagine we're a much bigger star. When you're a much bigger star, a much more dramatic process happens. You're still going to be burning some hydrogen in that core, and you're eventually going to run out of hydrogen. You'll run out, by the way, much faster, because what tends to happen is the bigger a star is, the more reactions need to happen to keep it that big, and volume doesn't scale with the mass, and so you're going to run through your store of gases a lot faster. And so that core of the star is going to run out of hydrogen, and it's going to go to helium, and it may expand out in this direction. So maybe you go to hydrogen to helium. Maybe you go from helium to oxygen. Maybe there are many different paths you can go, but you're going to start forming bigger and bigger elements inside that star. The core is going to keep making bigger elements. It's going to keep going up and up and up and up and up until you have silicon turning into iron. Now, again, these are big stars, right? Our sun doesn't have nearly enough mass to fuse silicon into iron. Nowhere near enough. But if you are 8 solar masses or bigger, then this is the kind of thing that can happen to you. Now, the cool thing happens when you start fusing that iron. When the core of your star turns to iron, a really interesting thing happens. Iron is a very special element for nucleosynthesis, for this kind of reactions and stuff. Iron won't fuse. Iron will not produce energy via fusion. It won't happen. I don't care how much mass you have. You have infinite amount of mass. Iron will not create energy. So whereas a moment before you had all of this radiation pressure pushing outwards, as soon as the silicon turns into iron, all of that is gone. Gravity is still there, and it's there with a vengeance. But the outward force of radiation pressure is gone. The outer layers of the star begin collapsing in on that core with a vengeance. There's so much mass. Gravity is the only force going on in this situation, and it starts collapsing in on itself. This is a very, very dramatic process. It starts collapsing in on itself. Now the core, when it starts collapsing in on itself, some weird stuff starts to happen. Neutrinos start getting shot out. Again, watch the video. They go into a lot more detail. But basically, the core explodes, and all the outer layers explode away. This is what's called a supernova. This is a very dramatic event in space. Okay, these are things you can see from Earth happening. This is when a very big star explodes. The outer layers are just exploded away in this giant explosion, big cloud. A lot of the very dramatic pictures you may see on the internet of space are leftovers from supernovas. Supernovas are how, we'll talk about this later, but any element bigger than iron was created in a supernova. Anything bigger than iron was created in the microseconds that it takes a supernova to explode. Now, supernova has occurred. Again, this is big stars. Supernova has occurred. Now what? Well, that all depends on the core. If the mass of the core is greater than 1.4 solar masses, so I'm talking the entire mass of the sun, the whole thing. If it's greater than 1.4 solar masses, by the way, this term is what we call the Chandrasekhar, and I do very much apologize for the pronunciation there, but it's the Chandrasekhar limit. At this point, the normal atoms, so you have the protons and neutrons, and outside you have the electrons. There is so much gravitational pull on this core that the electrons lose their own place in the atom. You see, we're taught in chemistry this thing called Pauli exclusion principle, and that every electron has its own space, has its own spot in the atom, has its own spin, its own orbital, that kind of thing. If there's enough force, the electrons lose their space. You see, this is what keeps the core of our sun from collapsing. This is called electron degeneracy pressure. This is the pressure that stems from the electrons wanting to keep their spot. It's why you can't smush things down more than an atom. Okay, you can't, there's a limit to how small you can squeeze things. Well, if the mass of the core is bigger than 1.4 solar masses, the electrons lose their spot. They're basically squished into the nucleus. And so what essentially you have happen is the electrons join up with the protons, and you get the entire core of the star is one giant nucleus full of neutrons. The proton plus the electron becomes a neutron. The core becomes a giant nucleus. It has the same density as the nucleus of any atom here on Earth. All atoms have the same density of the nucleus. That is the density of that core. We call this a neutron star. These are very dramatic things. They do different stuff, and I'm going to share some stuff about sort of some of the behaviors of neutron stars. But that might not be all. You see, you're a neutron star, great. Neutron star can't collapse it down anymore. It's just a whole bunch of neutrons. Like, how much further can you collapse, right? Well, if the mass of the core is greater than 3 solar masses, that's the mass of the whole sun. This is what's called the Oppenheimer. Apologize again for pronunciation and spelling. Volkoff limit. Core collapses the nucleus. Oh gosh, my spelling is atrocious. The core collapses the nucleus itself. And instead of every neutron having its own identity, we call this the neutron degeneracy pressure. See, the neutron star, it still wants to collapse. There's still gravity trying to smush everything in, but each neutron needs its own spot. So it can't collapse anymore. It's collapsed as small as it can. That's as tight as you can get those neutrons. Can't pack them in anymore. That's the neutron degeneracy pressure. Well, if you have enough gravity, though, you can. If you can overcome the neutron degeneracy pressure, you're going to make what's called, we use big font for this because these are very dense, these are very dramatic things, a black hole. Now, 2 misconceptions about a black hole. First of all, a black hole is not necessarily black. I don't know what color black hole is. We don't know. The reason we call it a black hole is when we look up in space, we see blackness. A black hole is a star where the escape velocity from the star, and in order to get away from that star and fly away somewhere else, you would have to be traveling greater than the speed of light. Right here on Earth, we can send rockets away from the Earth and they don't come back. Right? The Voyager probe is out past Pluto now. It's not coming back to Earth. It achieved escape velocity from Earth. But for a black hole, the escape velocity is greater than that of the speed of light. Well, you may ask, what can go faster than the speed of light? Nothing. So that means nothing comes out, and so we don't see anything. It looks black. The other word people have trouble with is the word hole. You picture the middle of a donut. Well, the black hole is not a hole. It's not a giant drain in space, having everything like the water going down the drain in your bathtub. It's not a hole. It's an object. It is I'm sure, perfectly round object. I couldn't tell you what it is going to be like on the black hole. A lot of our physics starts really breaking down at that point, but it is certainly an object. It has mass. Not only does it have mass, it has a whole heck of a lot of mass. It is constantly adding to its mass. All the stuff it's absorbing is adding to the mass of a black hole. Black hole gets bigger and bigger. It does give things off, but will not deal with Hawking radiation at this point. So, big stars. Because they're so big, they undergo a supernova. If the core of the star is greater than 1.4 solar masses, that's the Chandrasekhar limit, then we have a neutron star. If it's bigger than 3 solar masses, now we have a black hole. Please watch the videos attached to this lesson. There's some very well done videos going into a lot more detail than I can do in a short video here. And try out some of the problems I have for you for this week. Hope you all are doing well. Look forward to seeing you in our next Zoom chat. With that,